This is the second lecture from Chapter 7, and this lecture will focus on the properties of light and how we use those properties to give us information about the electron. I'm going to start off with really what we talked about in the last lecture, and that is the Bohr model. I had mentioned in the last lecture that Bohr's model was probably the first concrete step toward development of the quantum mechanical model of the atom. And that really focuses on better understanding the behavior of the subatomic particle, the electron. So Bohr, as you remember, contributed primarily that electrons are quantized, can exist only in certain energy levels. And so a lot of research was focused on more quantifying anything we can about the electron. And one of the ways to do that was to find what the energy gap was between the different energy levels that an electron can occupy in an atom. One of the things that we have found out, and I want you to look at this pictorial of the Bohr model, by doing studies, is that as you get farther and farther away from the nucleus, notice that the gap between energy levels decreases. Okay, so that's an important observation to understand. So if an electron, an excited electron in energy level, let's see, 1, 2, 3, 4, drop down to energy level 3, the energy it would emit would be a lot less than the energy emitted by an electron, let's say, that started out in 3 and dropped down to 2. I talked briefly about the movement of an excited electron back down to a lower energy level and the emission of light. I'm spelling it out a bit more in detail, and what I think is really fascinating is the knowledge that all light, absolutely every single source of light in our universe, is a result of an excited electron falling back down to a lower energy level and then emitting that extra energy it did have in the form of some type of light. And so here are the steps written out for you. And that's something you should be able to explain back to me as well as draw a picture. So step 1 says you have an electron in its lowest energy level, which we call the ground state. And if you give energy to an atom, it can either be light energy, heat energy, sometimes even mechanical energy. An electron can temporarily jump up to a higher energy level. It's not going to stay there because it's unstable. We call it, at this point, an excited state. So pretty quickly, that excited electron is going to drop back down to its lower ground state energy level, but the extra energy it possessed will be released in the form of light. Now, we call light, particles of light, we call, this isn't working still, photons. So here's a pictorial, and here are the steps that describe that, which you should make sure you're familiar with. It turns out that every element has its own particular spacing of energy levels, and therefore when we excite the electrons in various elements, they're going to give different wavelengths and types of light as the excited electrons relax. And so we can identify, they're called atomic emission spectra, but we can actually identify elements based on the atomic emission spectrum. You may have done, in high school, you may have done a flame test laboratory where you were given various samples of compounds, usually ionic compounds, and you put little pieces of them in a Bunsen burner flame, and you were rewarded with different colors, yellow, red, purple, etc. So that's a very similar type of thing. Every element as I said, emits different wavelengths of light when its electrons are excited. And so that, again, that's a way to identify various elements. So the first kind of quantitative mathematical equation we're going to tackle is something called the Rydberg equation. So Rydberg came up with a mathematical equation that can estimate the properties of the light emitted by excited electrons. And here's his equation shown right here. So let's make sure we understand the different parts of it. Lambda, of course, that's wavelength. And so I want you to make a note of the fact that this equation, oh, I shouldn't write with this anymore, it's not working right, solves for the inverse of wavelength. So when you get done plugging all the numbers in, you have got to flip the answer you get upside down so that you can get wavelength itself and not 1 over wavelength. So just keep that in mind. R is a Rydberg constant, okay, and represents the energy level. So think of the Bohr model and the various energy levels for electrons. Notice that the energy levels are squared, and also notice that the first energy level you enter should be the lower one. So if you have an electron moving from the third energy level to the second energy level, for example, you would put 2 in for the first n, 2 squared, and then 3, the higher energy level, in for the second one. So let's work a problem with this to give you an idea of how to do it. I would recommend that you go ahead and try to work this yourself by turning off the video, but I'm going to go ahead and work it out for you also. Okie doke, so plugging into the Rydberg equation, here's the Rydberg constant R, and again making sure that you put the lower energy value in first, so that'd be n equals 2, and the higher energy value last, n equals 4. Remember to square those values, and then turn these fractions into decimal form and multiply it out, and you will get that 1 over the wavelength is around 2 million. Now, the most common thing students forget to do is, in order to get wavelength, you have to flip this upside down. So wavelength is 1 over whatever you get from the Rydberg equation. So 1 over 2.057 times 10 to the 6 is, let's see, 4.86 times 10 to the minus 7, and the units out of the Rydberg equation for wavelength are meters. So there's your final answer. Okay, so now that we know that all sources of light are a result of excited electrons moving to a lower energy level, let's talk about the properties of different types of light and what those properties mean. I'm sure you've heard of the common types of light, radio waves, microwaves, infrared, visible, and ultraviolet light. All of these types of light are collectively called the electromagnetic spectrum, okay, electromagnetic radiation. And infrared, I'm not sure if you all realize, infrared light is actually heat. So heat is a form of light energy. And so, of course, each type of light has its own frequency and wavelength. So let's talk about what those two properties are. The distance between 2 points, 2 identical points on a wave, is called the wavelength. So peak to peak or trough to trough, that distance is wavelength, which is designated with a lambda symbol, and the units are meters. Frequency is how many waves pass a certain point in time. And so if a lot of waves are crammed into a small distance, that is a high frequency. Basically, frequency is how many waves per unit time. If the waves are very spread out and not very many wavelengths per unit time, it's a low frequency. So take a look at frequency and wavelength and tell me the relationship between those two. So if you have high frequency, what can you say about wavelength? High frequencies have low or short wavelengths. Low frequencies have large wavelengths. So there is an inverse relationship between wavelength and frequency. We can also express that relationship in a mathematical equation, and we'll be doing some math with this equation. This equation tells us that the speed of light, which we designate with a small letter c, and the speed of light is constant for all types of light, whether it's a radio wave or a gamma ray. The speed of light is 3.0 times 10 to the 8th meters per second. That's how fast a light wave travels through space. It has nothing to do with how many waves per unit time. That's frequency. It's just the speed at which the whole light wave travels through space. So the speed of light is a constant, and it is the product of wavelength times frequency. This frequency symbol kind of looks like a crooked V to me. So what that means, you can see that the relationship between frequency and wavelength is in fact inverse, because since the speed of light is a constant, if wavelength goes up, frequency must go down in order for the product of the two of them to remain constant. Here's a pretty straightforward example of using the equation we just learned. Okay, C equals wavelength times frequency. And this problem, it says find out the wavelength if the frequency is 4.2 times 10 to the 18th. So you need to get comfortable rearranging this equation to solve for whatever variable you're being asked for. It's asking us for wavelength, so if you rearrange that equation, wavelength is the speed of light divided by frequency. If you're the type that likes the magic triangle, if you don't care for algebra, let me show you that. So as long as you have C on top of the triangle, it doesn't matter the order that frequency and wavelength are in. And again, of course, when you use these triangles, what you do is you cover up whatever you're trying to solve for. So if we're trying to solve for the speed of light, it would be frequency times wavelength. In this case, we are trying to solve for wavelength. So if you imagine covering up wavelength, it tells you that's then equal to the speed of light divided by frequency. So anyway, back to the problem. See if you can solve that. I encourage you to go ahead and punch these values into your calculator. Get very familiar with doing multiplication and division with scientific notation in your calculator. I always have a small handful of students on this test that do poorly on the test because they have not practiced multiplying, dividing, particularly dividing with scientific notation, and they end up with answers with the wrong exponents. So if we plug into this equation, we're going to see that wavelength equals speed of light, which we know is 3.0 times 10 to the 8th. You'll often see that in textbooks. They call that 2.998 times 10 to the 8th. I just round it more to 3.0. And then the frequency was given to us. It is 4.2 times 10 to the 18th. Okay. And when you plug that into your calculator, you should get the wavelength as 7.1 times 10 to the 3, 6, 9, 11. 10 to the minus 11. Now the units out of this equation are meters for wavelength. Okay, so hopefully you notice, though, before jumping to pick A, that this problem asks for the wavelength in nanometers. So there's one more step. We have to convert from meters to nanometers. So if we have 7.1 times 10 to the minus 11 meters, we're going to do a conventional unit conversion. And so we need meters in the denominator. And so 1 meter equals 1 times 10 to the 9th nanometers. So if you don't have that conversion written down any place, you'll want to do that because that'll pop up a lot in this unit. So meters canceled, and if we go ahead and do that conversion, we end up with an answer 7.1 times 10 to the minus 2. And now we have units of nanometers. And so the correct answer is right here. Now, of course, it doesn't have to be in scientific notation. So if you got 0.071 nanometers, that's just as perfectly correct. Alrighty, something that you might see mentioned, particularly in the ACS final, is it's something to do with the photoelectric effect. That's some studies that Einstein did, which supports that electrons are in fact quantized. But the bottom line is Einstein took a piece of metal and he subjected the metal to energy in the form of light. And when the light had a certain energy, and only when it had a certain energy, electrons would get displaced from the metal. But it doesn't, if he had a light that wasn't enough energy, no matter how long he shined it on the metal, he could not eject any electrons. So he needed a certain frequency and energy of light to eject any electrons. And that certain frequency and energy depended on the metal that he used. So the bottom line is the electrons really are bound to the atom with very particular energies. And unless you subject that atom to precisely the right energy level, the electrons aren't going anyplace. So that's called the photoelectric effect, just so you are somewhat familiar with it. So as a result of that, Einstein came up with yet another equation to describe the energy of light. And let's go over the different parts of it. So E stands for energy, of course, and energy, the most common units we work with are joules, and joules is abbreviated with a capital J. And H is Planck's constant, which I'll give you, of course, but you may want to jot down to be able to work the problems. 6.626 or 6.63, depending on how you round, times 10 to the minus 34. It has very weird units of joules times seconds. Okay, just a proportionality constant. And then the V, or correctly called nu, is frequency. So basically what Einstein's equation is telling us is that energy is directly proportional to frequency. As one goes up, the other has to go up. And then H is just a proportionality constant. And so we learned that that wavelength and frequency are inversely related. Energy and frequency are directly related. It's also worth mentioning that we mentioned earlier, and it actually was Einstein that said a light has not only wave properties but particle properties. And so as a result of his work, we call a particle of light a photon. So often when scientists see this, we call it H nu, they call that a packet of light energy or a photon. Here's a question that'll get you to think a little bit more, hopefully, about the photoelectric effect. So let's say that we were exposing a certain type of metal to yellow light. Now, yellow light has a certain energy and frequency. It's a type of visible light. And we know that it requires light of at least that energy to eject the electrons from the surface. So what would happen to the surface of that metal if you exposed it to ultraviolet light? I'm hoping you know that ultraviolet light has higher energy than any type of visible light. So what happens to those electrons that require yellow light, at least yellow light, to be ejected if you expose them to a higher energy light? Take a minute and look through the possible answers. Turn the video off for a minute and see what you would pick as the answer. And then we'll go through each one. Well, the answer is not A, because we know that the light has at least enough energy to eject. It's higher energy than yellow light. So B, electrons would be ejected, and they would have the same kinetic energy as those ejected by yellow light. Well, the first part of it's correct, but they're going to have some extra energy. It's not going to be enough energy to necessarily eject more tightly held electrons, but certainly the electrons that get ejected are going to have more oomph to them, kinetic energy. So let's look at C. Electrons would be ejected and they would have greater kinetic energy. Yes, that sounds about right. D says electrons would be ejected and they would have lower kinetic energy. Well, that's just kind of silly. So that might be the type of multiple choice question that you could possibly see in the ACS type final. So the equations we have so far that give us information about the type of light we're dealing with are these two equations. And as somebody pointed out to me in class, I combined them wrong here, so please don't write that down. I'll do that manually. All right, so if you combine these two equations, you get what we call the combined light equation, which is energy equals Planck's constant times the speed of light divided by wavelength. Okay, so you have the two constants on top and wavelength on the bottom. Now, let's imagine that you were given a problem that gave you, well, let's say that they gave you energy and they asked for a wavelength. How are you going to figure that out? Well, you could either use both of these equations. You could use the energy equation to first solve for frequency. Then you could plug frequency into the second equation and solve for wavelength. Or if you happen to remember this combined equation, you could solve for wavelength directly in one step if you knew energy. So you definitely have to commit these first two equations to memory, but it is handy for a lot of people like to also remember this combined equation. Here's a typical sample problem. So you can either treat it as a two-step calculation using each of those equations. Let me just write them again here. Or if you happen to want to try to use the combined equation, you can do that also. Let's go ahead and see what you get. Pay attention to what they're asking. They're asking for nanometers again. And the constants you should have handy as you work these problems out are the speed of light and Planck's constant. Okay, so give it a try. It's another good one just to punch in your calculator and to make sure you're using your calculator correctly. And then on the next page, I'll work it out for you. So if I go ahead and use both formulas in a two-step calculation, I'm going to start with the energy formula because we were given energy, right? So if I plug in for that formula, energy equals, this is Planck's constant, times frequency. I'm going to rearrange that equation to solve for frequency, And I get then that frequency is 6.66, that's evil sounding, isn't it, times 10 to the 14. Units for frequency are 1 over seconds, or you could put hertz. But the problem's asking for wavelength, not frequency. So I have another step to do. So we'll call that step 1. Step 2 is I'm going to use the second equation, which will get me to wavelength. So I'm going to rearrange that. I'm trying to solve for wavelength. So wavelength is the speed of light divided by frequency. And so speed of light is 3 times 10 to the 8th. And frequency that we just solved for is 6.66 times 10 to the 14th. Again, please plug this all into your calculator to make sure you're using scientific notation correctly. And when you do so, let me just double check myself. You get an answer of 4.5 times 10 to the minus, 367. Now remember, you get meters out of these equations. Okay, so now we have to convert to nanometers. So 1 meter equals 1 times 10 to the 9th nanometers, which means our answer is 450 nanometers. So that's it for the second lecture from Chapter 7. The third and last lecture is called Orbitals and Quantum Numbers.